So I'd like you to please welcome our next speaker, Marco Prisco, full professor at the Department of Civil and Environmental Engineering at Politecnico di Milano. His main research interests are constitutive modeling of advanced cement-based materials, reinforcement concrete interaction mechanisms, sustainable design of RC and PC and FRC structural elements, prefabricated structures, and the structural response at exceptional loads. He is author of more than 350 papers and coordinator of many research projects financed by private companies, regional and national funds, and European community. He is series editor of Springer Tracts and lecture notes in civil engineering for Springer Nature, honorary editor of ISI Journal European Journal of Civil and Environmental Engineering, presidium member of FIB, member of several national and international technical committees, and coordinator of the Committee for Model Code 2020 chapters on FRC and of RILEM Commission TC 288 on impact and explosion. He is currently convener of the Commission to introduce FRC in EC2. Since 2018, he is the technical director of the design company DSC Urba SRL. Please welcome Professor Marco Prisco.
Thank you very much. Can you hear me, first of all?
Yes, we can. Thank you.
Thank you. So thank you very much, Carrie, for the nice presentation. The title of this short lecture corresponds to the outlines of my brief speech. I would like to sketch the bridge Italian situation, and then I would like to present 3 case studies, the research in progress, and a rational approach to select intervention priorities we are working on with the Politecnico and the Regione Lombardia. In the last 9 years, we saw in Italy 9 collapses of bridges. And you could see that the collapses marked with the orange dots were mainly man-made hazard, while the other collapses were due to the natural hazard. If we look at a snapshot given us and presented a few years ago by Philippe Yen in Politecnico di Milano, looking to the US highway bridges, you could see that you can have essentially 3 different categories. The yellow, which don't present any deficiency, the blue, which correspond to the functional obsolete bridges, and the light blue, which correspond to the structural deficiency. And you can see that when we overpass the 50 years, the ratio between the light blue and the total length of the bar is becoming much more significant. And this means that after 50 years, effectively, there is a strong need of control and restoration. Looking to the bridge failure causes observed in 32 years from 1980 to 2012, we saw 1,062 failures over 600,000 highway bridges. And you could see that flood was the most important cause with about 28%. If we look to overload, we count only 13%, while collision and score were more than this, so 19 and 15%. And internal, that means mistakes in design on the execution counts around 11%. All the others arrives no more than 15%. Obviously, this means that the risk can be mitigated only if the collapse causes are suitably taken into account. If we look to Italian situation, we have a huge difference between railway system and roadway system. In fact, if we go in detail, we see that in railway system, we have around 21,000 kilometers against more than 800,000 kilometers for roadway. But the most important point is that there is one main agency, RFI, which controls 83% of the total net. While for roadway, we had only as main agency ANAS, which is able to control only 3.5%. That means a much more heterogeneous situation in roadway system. And our geography causes a situation where you have one bridge every 3 kilometers for railway and one bridge every 2 kilometers for roadway. You could note also that a few years ago, ANAS observed that about 1,500 overpasses on highways do not have a recognized owner. So this is a main difference between the two systems. If we go in detail for the highway bridges, about 2,000 highway bridges for, you could see that the historical wave is also classical of Italian situation, and the major amount of bridges were built between 60s and 80s. And you could see also that the materials have strange waves because you have RC construction that progressively reduces, pre-stressed concrete construction, bridges that that represent a very important portion even now. And in the last years, we observed an increase of steel bridges. And even in this situation, we have about one bridge over 1.5 kilometers. Looking more in detail with the span length, we have an average value of 24 meters. We have as a majority more than 85% of bridges with a span lower than 35 meters. And you could see that the couple beams represent the main typology. We have also some arch before the 60s. We have also some caisson between 60s and 2000. And always we have some fixed slab, which represent even now a certain significant percentage. About the static scheme, we have a mainly simply supported situation. We have continuous beams only starting from 80s and the depth end that arrive essentially from 60s to 2000. If we look to the risk associated to different construction in a slide presented for the first time by Aurelio Muttoni in the FIB Symposium in Melbourne 2018, we could see that the failure frequency per year for a bridge is not so different with respect to other type of construction like dams, like pressure vessel in ships, like nuclear power plants, or even space shuttle or airplanes, commercial airplanes. And you could see that the situation as shown by Philippe was practically in the same range. If we had one bridge failure per year in Italy, we could be in the same range. What is very important to observe that is the risk is strongly associated with the amount of resources given for the maintenance of the bridge. And according to Swiss computation for highway, it is the highway bridges need about 400 euro for kilometers and per year. So it's much higher than what we did in the last year in Italy, about one order of magnitude. Let me speak about 3 case studies that I had the chance to examine in detail. The first one is a very old bridge, Azzone Visconti, that was built in the 14th century. And it is probably the bridge that was painted by Leonardo da Vinci in the famous Gioconda. This type of bridge is a stone bridge, and there are also some portions built in the 50s, which are made of reinforced concrete. The second one is Mella Bridge, is built in the outskirts of Brescia. It's perfectly functioning. It is post-tensioning, cast on site, and it has a global length of 42 meters and 3 spans. The final one is Annone Bridge that was built in the 60s, and it failed in 2016. And you see the picture before and after the collapse. And it was built by means of prefab beams, pre-stressed, and also cast on site concrete for the top slab and the diaphragms. Well, looking to the first, we were able to see which are the uncertainties that you could have in the analysis of ancient bridges. As obvious, this type of bridge was built and rebuilt in a lot of time, so historical situation and presentation is very, very important. And you have also the possibility to analyze very well the soil, because this very stiff bridge depends a lot on the soil movement. And we did a care investigation on that. We analyzed the bridge essentially because we were finalized to compute the bearing capacity of the bridge by means of 3 steps: the advanced diagnostics, the controlled static test based on a model, a 2D model, and then the control of the 3D model by means of dynamic test to control the stiffness, and all the information, even concerning the degradation of the bridge, was collected in a BIM model, pardon. The Mella Bridge was a lucky bridge because it is a good condition, and for it we have disposal original design report, original technical drawings, photos, inspection report, and also a last inspection that was done in about 5 years ago. This is a very lucky condition, because if you compare with other type of bridges in Lombardia, we have only 67 over about 400 bridges in this condition. All the other, you could have a much lower amount of information. Even though we had also the possibility to analyze the crack pattern, you have also some intralinear cracks. We have also carbonation with about 6 centimeters in certain point. And we observed that we could need a monitoring, a static monitoring. So we measure the displacement, and we observed that the daily traffic produce a displacement of about 1 millimeter, which is comparable to what we observed when a exceptional load with 380 tons crosses the bridge in the center of the line, along the longitudinal axis of the line of the bridge. And you could see even here that you had around 1 millimeter. So this incredible amount of load produced essentially the same displacement. That was not exactly what we computed by means of elasticity, of course, because in elasticity we had only 0.77. What is important here to observe that even in this situation, for a long time, the bridge was crossed by exceptional loads, believing that you had only 7 beams, but in reality you have only 6. So there is a huge difference between as-built and the original design. And also carbonation represents a problem, because we don't know how carbonation could evolve in the future. The last bridge is Annone bridge. It was collapsed, and the balance was 1 killed and 3 injured people. And it collapsed when the truck of about 108 tons introduced a hole in the middle span. And you have to consider that this load can be compared with the total load of the middle span, which is about 172 tons. That means a huge load with reference to the dead load. A Google Map picture given about 4 years before the collapse already showed clearly a very important damage. But this was not enough in order to prevent the collapse. What it's important to say is that the bridge is a 2-class bridge and a 2nd-class bridge, pardon. And so it was designed to bear around 36 tons, but in the reality, we had for about 7 years 108 tons. So it essentially was able to resist for a long time, but at the end it collapsed. And you could see also that in the time, the total load, according to the national standard, increased a lot. So if you look in the time, and if you compare the green line with the blue one, you have the difference between what it was designed, it was planned for design at the construction time in the 60s, with respect to what we ask now. It's important to say that also in this case, there was a even a small mistake, but in this case, as-built was different, and so the as-built situation increased the safety of this bridge. Which was a reaction to this very important collapse that was strongly observed by media, and also after 2 years, the impressive collapse of Morandi Bridge. The reaction was a project in Region Lombardia with our Politecnico immediately after the Annone collapse, and then a strong increase of year budget for bridge maintenance, about 1 order of magnitude after 2016. And then there was also the national guidelines issued by our Minister of Transportation in 2020, and recently also a strong correlation with the Minister of Transportation as the National Research Project. The name is Ray Lewis, which correspond to the first time where there is a strong connection between the minister and a research team of university, of about 22 universities. And the global amount of money was, in 2 years, was 15 million of euro. And with these guidelines, there were fixed 4 different levels of attention, starting from the simple chances of infrastructure to the preliminary evaluation of the infrastructure and to the accurate verification. In the Lombardia Politecnico program, we went to there for the problem. So the idea was to identify the priorities, to plan the interventions. And we presented a bridge identity card with about 90 data entries. We worked with the 12 province technical office that appeared very heterogeneous, and we were able only to complete about 76% of the total bridge selection set. And we have also in this situation a prevalence of RC and PC average span with respect to the other. And we tried, starting from the technical description of the structure, the technical features, the historical data, hydraulic data, which is very important, the functionality data and the exposure data, by means of elaboration, by means of logical and algebraic operators with calibrated rules based on expert judgments to fix 4 levels of attention. The 4 level attention were also completed with a free set of level of completeness, which is very important because the data that we have are only documentary data, and they are not absolutely homogeneous. So we need to distinguish between these 3 levels of completeness. At the end, we try to correlate the functional priority class with the technical priority class, and we arrived to select 4 different classes that start from the urgent need of reclassification to the regular inspection activity, passing from the need of reclassification or even inspection priority. For the Mela Bridge, we are here, and you could see that for 8 bridge, we have also the need to introduce monitoring, and we are working on it. For the concluding remarks, I could say that the bridge failure of the last years correspond to a quite high risk, also aligned with other accepted risk. Only a significant increase of maintenance resources will be able to progressively reduce it. The bridge construction wave, scantily documented, will require strong effort to improve diagnostic devices as well as durability and retrofitting research. There is an urgent need to suggest prioritization rules to suitably canalize the first available resources. The introduction of careful maintenance plans should homogenize maintenance policies to control bridge serviceability and safety during their life. That does not coincide with that adopted to define the design loads. And finally, a clear definition of roadway corridors for exceptional load tracks could allow an important resource saving. I would like to leave you with this picture where I designed recently an FRC and the HPFLC bridge with such kind of class, so 2 very high performance material. And the bridge is a small bridge with only around 70 meters over a small river, with a ratio of the span length with respect to the depth of 27, it is a post-tension in the longitudinal direction and partially in the transversal direction close to the 6 support. But I would like to remark that the cost increase due to the introduction of this durable material correspond to around 5% more of what we could have without. And if we consider, if we compare this increase of cost of 20 euro with respect to the maintenance cost, it corresponds only to 3 years cost. Thank you for your attention.